All right, welcome everybody. Thank you so much for coming today. Today, I am so excited to introduce you to our distinguished speaker, Dr. Zachary Del Rosario from Olin College of Engineering. Zach is an assistant professor of engineering and applied statistics at Olin. His goal is to help scientists and engineers reason under uncertainty. Dr. Del Rosario he started as a technical researcher working on statistical procedures for engineering design, and now uses qualitative research methods to understand how engineers deal with uncertainty in practice. And as he'll show us today, hope students understand the same. So please join me in welcoming Dr. Zach Del Rosario.
Thanks, John. Let's see if I can get this in a reasonable location. Do you need me to do a mic check or should I just go for it? All good. Thank you. All right. Hi, folks. Thank you for the introduction. As John mentioned, my name is Zach. I'm coming to you from Olin College. I'm both a professor there now, and I'm also an alum. I graduated there as an undergraduate in 2014, and now I'm back as a faculty member. This talk is really about the intersection between data science and engineering. This comes out of some experiences I had originally training as a technical person, like doing a PhD in aerospace, developing proofs and algorithms and all these things, and then seeing just utter mystification when it comes from practicing engineers. I remember when I was talking to folks in industry about this stuff, they would tell me things like, what uncertainty are you talking about? Does this thing actually exist? And it ended up launching me into basically pivoting and retraining as an education researcher. So what I'm going to tell you about is the overview of a years-long project. So this is going to be a mixed methods project that's going to go through a couple of different phases. And we are ultimately going to talk about this idea of targeting variability. It's a term that I'll define later. But to preview it, the core idea is this is a beneficial behavior that I think we should be thinking about when it comes to engineers working with data, or really working under variability. Put briefly, targeting is just the idea that the variation we see in the world is actually entering into engineers' decision process in some way. We're not just ignoring it, we're actually engaging with it. But to illustrate why I think this is important, I want to start with a story. So the best story I've found that illustrates the importance goes back to the 1950s. At this point, the US Air Force had a really serious problem, which is that their aircraft were falling out of the sky. At the time, command blamed pilots. They said, we've just introduced jet engine technology. These aircraft are more performant. They're more difficult. Our pilots are just not skilled enough to actually handle them. But there was a researcher by the name of Gilbert Daniels who had a different theory. You see, at the time, aircraft were designed for the average man. And already, this suggests some problems to us. This is coming from an era when the possibility of female pilots was not considered. It's already giving us a hint that there's probably something wrong with this design approach. But even if we dig into that, even if we think about designing for the average man, well, we need people to be average or close to average in order for this kind of system to work. So Gilbert Daniels asked, out of the number of pilots that we've measured so far, how many of them are actually average? This is a fun question that I love to ask people. How many do you think were average? Any volunteers? Over here? 0. Okay, I hear 0. Any other guesses? 17, very precise number. Any other? 40%? Okay. So maybe we could make a statistical argument and appeal to say maybe the bulk of people land close to average, perhaps. So I'm hearing a variety of answers, maybe 0, maybe 17, maybe about 40%. You've actually seen my slide deck, so I feel like you've cheated. But it's a striking answer. It was precisely 0 people. This is something that's really surprising at first, but when we unpack it, when we unpack what it means to actually be average, it starts to become a little bit less mysterious. Well, what do we mean when we're saying average? What we mean is not just average on one dimension, but average on all of the dimensions that matter for doing something like operating an aircraft. What the US Air Force did at the time is they measured height and weight and reach and torso girth and all of these other factors that matter for actually sitting in an aircraft and being able to manipulate all of its controls. They took the average and they designed just this one fixed person. And indeed, if we think about just one dimension at a time, we'll probably see maybe 40% of people land close to average. But what we're saying is simultaneously, that basically never happens. And it's because of this variability across multiple dimensions that truly no one is average. The resource I drawn for this is from a book by Todd Rose, and he does a really nice job connecting these ideas to education, basically pointing out that people are variable, not just in our physical, but in all these other mental characteristics, something that shows up within, say, engineering practice. And there's a lot more that I could say about this, but I want to pivot over to here. Now that we understand this problem, it's the multivariate nature of variability, the solution's actually pretty simple. If people are different, let's just design for variation. Let's say just design adjustable seats. Question over here. Yes, that's literally what they did. They truly designed for the average man, welded the seat in place, assumed that everyone would be near average, which is why planes were falling out of the sky. But it's kind of wild that this sort of mistake, this sort of thing that we take so for granted now, was an encoded design flaw at this point in history. This sort of issue is comprehensively solved. We know how to design average seats. But problems of this character still show up even to this day. So for instance, in a fairly recent study, Bose and others found that females in the United States have about 50% higher odds of suffering a severe injury in an automobile crash. And the Government Accountability Office points the blame at crash testing practices. So even today, the standard practice is to use a scaled median male dummy in order to represent female bodies. So completely ignoring the systematic anatomical differences across people that actually lead and contribute to these kinds of disparities. In my own work with some of my research students, we ended up doing a scoping review of engineering textbooks that are presently used to teach classes. We found that only about 11% of them mention variability. And this last piece, this is the study now that I'm going to be telling you about. In doing interviews with practicing engineers, we found that some of them will actually neglect variability. They just won't account for it in the design decisions that they're making. So this is a problem that still shows up, even though we've seen these kinds of statistical problems play out in engineering before. So what's the rest of this talk going to be about? It's going to come to you in 3 parts. Part 1 is going to be about engineering practice. I'm going to tell you a brief summary of a qualitative study we did with practicing engineers. Then we're going to go into part 2, measuring targeting. As this hopefully implies, this is transitioning to a quantitative project. I've spent the past couple of years now working on developing an instrument, a survey to try to measure this kind of behavior in practice. And then finally, a short part 3 is coming back up to talk about, well, what can we actually do with any of this? What are some tips for teaching practices based on the work that I've done so far? Main punchline I want to give you is that I actually think that US adults are generally quite adept at thinking under variability, but certain engineering practices, especially reporting practices, end up hindering the underlying good decision making. We'll get there by the end. So part 1 is all about engineering practice. So at the beginning of this project, back in 2021 or 22, when I was initially planning it, there's really no theory to guide or ground any of this work. There wasn't even really language to describe these kinds of issues. So my initial goal was really to develop a conceptual framing of how engineers make decisions under variability. So towards that end, I carried out a qualitative study. I recruited a sample of 24 practicing engineers. So these are folks with substantial engineering, like industry experience. I ended up focusing on aerospace, civil, and mechanical engineers for reasons of interview protocol design. And we carried out clinical interviews. This is a particular style of interview where you pose basically tricky problems to participants, and you use that as a way to see how they make sense in tricky situations. We had 9 tasks. We presented them with both data and an engineering context. And what was key in all of these tasks is that we had variability. Variability that came from material property. This is partly why I chose to focus on these particular disciplines, because all of them include some content on structural engineering, structural design. And then we used an open inductive coding approach to analyze the data and arrive at a framework, which I'll tell you about here in a little bit. As an example of one of those tasks, this is coming directly from that interview protocol, a slide that we presented to all of our participants. Here, we've got some task over here, and we've got a data set, just 10 observations on a material from the same material, but multiple realizations. So here, we're asking participants, here's a situation. You've got a load-bearing design. You've got a component in simple uniaxial tension, kind of thing that looks a little bit like a textbook problem. How would you use the data to describe this alloy? We saw a few different patterns of response. One is some participants would, honest to God, say, I'll just take the mean. Full stop. Some participants would talk about the mean, but also talk about variation, saying, maybe I would compute a standard deviation. Maybe here are the minimum and maximum values in this data set. They would engage with the variability. They'd at least acknowledge it. But what is the most beneficial, the most sort of sound engineering practice we saw were cases where participants would say, well, I'm going to think about something like a worst case. This is a strength. So what would be the worst case is if the material is weaker than it typically is. So I'm going to find some way to get at a lower value. Say, I'll take the average and subtract off 2 standard deviation. Some participants would actually just look for the smallest value in this table. That would end up being this 155.6. In any of those different approaches, they're targeting variability. They are acknowledging that variability, but they're bringing it into their decision-making process. So this is ultimately what we produced from this study, the neglected, acknowledged, or targeted NAT taxonomy. This is a way of describing these different kinds of responses that engineers have when they're exposed to statistical variability. Here's some examples coming from that. Oh, sure. Okay, let me check to see. Let me make sure I'm not zooming too fast here. I get excited and start running straight ahead. So here's some examples coming from our interviews that illustrate these different points along the taxonomy. Here you could see reading the initial prompt to this participant. I'm asking him, okay, you're going to design a rod to withstand a particular load using this data set. How would you use the data set to help design the rod? And this participant did the same thing that he was doing throughout this entire interview. He kind of laughed and he said, I'm going to go with some assumptions and then I'm going to take the mean of these 10 samples. This is kind of the classic way of neglecting variability, taking an average, not bringing variability into your process at all. And like we saw with that average man example, this is potentially dangerous. With something like structural design, if we're designing, assuming this middle case, what happens when we have to pull something off the shelf that has a strength weaker than what we typically see? That's potentially a safety hazard. So a contrast, this is now a targeted example. Here I'm asking a participant, this is partway through an interview with her, would you also compute a standard deviation like you've talked about before? And here she talked about, yeah, so since this is load bearing, I would want to be at least 1 standard deviation below the tensile yield strength to make sure it never deforms to the point where it won't return to its original value. Now giving us an idea of what targeting looks like. Note, they're thinking about variability. Here, she's doing this specifically using standard deviation, but she's also connecting it to consequence, saying, I want to make sure it never deforms too much. So this is core to this idea of what it means to target. One needs to first acknowledge variability, but then they need to go further. They need to bring that kind of statistical thinking into their engineering practice. So it's a necessary but not sufficient condition to at least think about the variability, but then to go and do something with it. Okay. This is good. We now have some language to actually describe the different kinds of behaviors that engineers have variation. Engineers will either neglect, acknowledge, or target variability. But at this point in the project, we still have some remaining questions. This targeting thing, I would argue, is good. It's the kind of thing that can help us to avoid those sorts of average man errors that we saw earlier. But is this rare or is it common? And also, what are some factors that either promote or hinder targeting of variability? And this is where we run into now basically some methods issues. If we want to ask more inferential questions, if we want to ask how many, well, going out and carrying the most cost-effective way. So part 2 is about going from this qualitative study and moving towards something that we can use to start to measure this kind of behavior at scale. So was that, and yeah, absolutely. Mhm. Yeah, yeah. It's the sort of thing that opportunistically came up in some of the interviews, say, what kinds of things have you seen before? It was not a primary focus of this. Some of the other work that I've done more directly with students, I've gotten a chance to look at things like classroom practices that ultimately promote or hinder thinking about variability. We could talk more about that. Yeah.
Interviews was people working in industry, right?
People who are in industry. Yes. Sorry, that may not have come through. This was with practicing engineers. Yeah. We could talk later. I have done other work with my students to try to get at some of those more classroom-oriented details, like what kinds of experiences in the classroom lead to your conception about variability or other topics. Yeah, this first project was really about at least characterizing this kind of behavior. Because again, at the beginning of this whole project, we just didn't have language to describe the kinds of behaviors that we would observe. So part two is about taking this conceptual framing, this neglected, acknowledged, or targeted framework, and actually developing some way to measure this behavior at scale. Our goal was to start to look at things like frequency and factors that affect these kinds of behaviors. And for that, we really need an instrument. So this was all about survey developments. We did many pilots over multiple years now at this point. And actually, we're finally at a point where y'all are going to be some of the first people that I get a chance to share that with, because I think we gathered this sample at the beginning of March. And so this is the first time where we really feel confident with an instrument that we believe is both valid and reliable for measuring this behavior. So the study population now is not just engineers or practicing engineers. It's actually US adults. We decided, since actually recruiting engineers is kind of difficult, and also it's a phenomenon that's maybe of more general interest, we decided to expand the scope of this to look at US adults. And with a survey vendor, we actually gathered a representative sample. 306 participants is what we had in total. And because we were looking not just at engineering problems anymore, we actually had to design tasks that are really everyday scenarios that happen to have statistical variability. Here's one example of that. Let's imagine we're doing an auction. So in an auction, a painting receives 100 bids with an average bid of $1,500. Guess the bid that would guarantee you win the painting without paying too much. Here, we are choosing a situation that naturally will have some variability. I think most reasonable people would not assume that everyone happens to bid exactly $1,500. So there's a source of variability that's a fairly, we use the term ecologically valid. It's the kind of situation that most people would run into in their lives. Also, if you bid $1,500 here, you're probably not going to win this auction. since there is variability, we have a way now to see if you're guessing just the average or if you're guessing something else. We can actually judge whether or not you are targeting the potential consequences of that variability. So had 10 such tasks and 3 treatments. We had multiple different tasks so that we had repeated measures within each individual. And we asked participants for a numeric answer, say, how much would you bid in this auction? We also asked participants, what do you think are the highest and lowest values in this situation? Say, what do you think was the lowest bid or the highest bid? This gives us a way now to actually measure what is their perception of variability. Do they think it's, say, very, very tight? Do they think that it's wide? And also, where does their answer land in relationship to their own perception of the problem? We also had treatments. We randomized participants into one of these 3. Those here on the next slide. So the text treatment is what we saw earlier. It's just a text description of the scenario. But we've got 2 different variations on this. One that actually shows a lot of information. This is those 100 dots. So we're showing each and every one of those bids. Using this, a person could probably figure out what the correct bid is. Actually, let's try this. What would you bid if I told you these are all of the auctions that are currently in play? 2501, exactly. That would be the correct answer over here, just slightly over the current highest bid. That's how you win an auction. So over here in this Sinoplot treatment, a person actually has more information to leverage, whereas down here in the bar treatment, we're showing exactly the same average, and we're actually potentially giving them a little more information. We're showing them the same scale over here that we would show in the Sinoplot treatment. We're not calling special attention to it, though. We had the expectation that we would actually see decrease because we've got more information here. We've got, sorry, this is a lent clicker. I'm clearly not used to it. This text treatment over here is giving less information. This bar one, despite possibly giving more information, actually has some known, let's say some known fallacies associated with it, one of which is called the bar tip limit error. So this is something that actually my collaborator on this project, Jeremy Wilmer over at Wellesley College, has identified. When people report averages using bar charts, sometimes people misinterpret this as basically count charts. Some people will look at a bar chart like this and think all of the data lives below here. But if all the data were actually below this bar tip over here, the average would actually be down here. So it's a reading of the chart that is inconsistent with the information being presented, but it's a pretty common misreading. In studies Jeremy has done, he's found that, say, between 20 and 30% of participants will actually commit this kind of misreading of an average bar chart. So we think that due to this bar tip limit error, we'll probably see worse performance over here. But even with providing more information, it's unclear to what degree a typical US adult can actually make use of something like this. There's actually open disagreement in the data visualization community if you should just use simpler charts like this or actually show all of the data. Can people actually make sense of this stuff? We thought they could, but we wanted to test. I remember when I showed this average bar chart to my wife, practiced this presentation with her, she was like, people don't actually do this. They don't actually show averages using bar charts. It turns out these are pretty common. In some literature, in things like in psychology or education literature, you often see these, and also in graphs aimed at a lay audience. If you'd like to see more lit review on this particular topic, in this paper that Jeremy published back in 21 in the Journal of Vision, he actually does a nice job reviewing where these things come up. I see. Go ahead and take the photo. I've got the references slide at the end, which I can also flash. You might find that one helpful. So these mean bar graphs actually do show up in the wild. They're often used to report simple numbers. How are we actually gathering information from our participants? So here's that same text-only auction stimulus that I showed earlier. We're telling them some basic facts about the situation. We're asking for a few pieces of information. We're asking for the lowest value, their perceived lowest value, guess the lowest bid, their perceived highest value, guess the highest bid, and then also their answer. So in this case, guess the bid that would guarantee you win the painting without paying too much. Say a participant might give this value over here, hopefully within the range they reported. But there's a ground truth. Since we've set up all of these tasks to have a known minimum and a known maximum, we know that there is some true highest value have a correct answer, which gives us a fairly objective way to see whether or not a person is answering the question correctly. We've got a problem here, though, with some of these tasks, with specifically the text and chart treatment. We haven't directly told them all the information they need to get the answer exactly correct. So we do a mapping. We do a mapping in order to account for the fact that participants basically have their own perception of the problem. We take what they perceive as being the lowest and highest values. We use that to map everything to the unit interval. And we do the same with the ground truth data, which gives us a much more fair way to compare those two answers. So on this normalized scale, we compute what we call relative error. And if that's less than 10%, then we say that this is a targeted response, a strictly targeted response in a very precise way. Now, that can be somewhat difficult for our participants to achieve, so we basically give them partial credit as well. So if a person guesses at least on the correct side of the average, say the correct answer is over here, participant's answer is over here, it's maybe far away from the true thing, but at least it's on the correct side of the average, then we say that's also targeted, but in a side sense. So we've got two ways, a more strict and a less strict way of judging correctness of participant responses. Okay, so what does it actually look like given this coding of the data? One of the top level takeaways that I have is that targeting is actually pretty common in everyday scenarios. Let's unpack this graph. So here on the vertical axis, I'm showing you percentage of participants. So from 0 to 100, this is where we add up to everyone, but we are breaking down all of the participants in a particular treatment according to how many tasks that they targeted on, how many that they at least guessed in the correct direction, or maybe even got very, very close to the right answer. Green here is showing you all of the participants who got 10 out of 10 correct. They aced this. This blue bar over here is showing participants who got a majority of them correct, anywhere between 6 and 9. Yellow is where they got a minority correct, so anywhere between 1 and 5. And then red is where they got 0. So some things that we note, this 10 out of 10 performance is decreasing as we go from sinaplots to text to bar. That actually conforms to our expectations that participants tended to do best when provided with more information, tended to do worse when we gave them bar charts. And what we see, especially these 0 out of 10 cases, are most prevalent in the bar chart treatment. This is striking. This is the set of people who didn't even guess direction. So here, this looks like a set of folks who were actually quite confused. From what we're going to call a null model. This is a simulated data procedure where we are randomly drawing a low and a high value, and then we are randomly drawing a value uniform at random from within those upper and lower bounds. So this is what it looks like if a person is not targeting, but at least guessing reasonable bounds. What we tend to see is that we do not find any 10 out of 10 cases over here. We also don't find any 0 cases over here. So this gives us a reasonable baseline for what guessing at random might look like. In particular, we tend to see a lot more folks who are capable of understanding the task than we would see under guessing completely at random. So at least people, one of the worries we had with this was designing tasks that we thought people could actually understand. This is the sort of thing that helps us to believe that these tasks are actually ecologically valid, that people are able to make sense of them and are able to exhibit patterns that are beyond just randomness. So that was at the top level, so looking at all 10 tasks. Now let's drill down to just one of the tasks, that auction task I mentioned earlier. So First thing I want to note is that bar charts do seem to do more harm than good. What we see over here, these red bars are showing us the number of folks who committed the bar tip limit error. That is, since we asked for what each person thinks of as being the largest value in that scenario, we can check to see if that's at the average or lower. If they're reporting that as being the highest possible value, that's the bar tip limit error. And what we see is considerably less targeting, this light gray over here, that has decreased. So fewer people are guessing even in the correct direction. And we're seeing quite a bit more of this bar tip limit error. So bar charts seem to do more harm than good, but also sign plots seem to do more good than harm. This solid black over here is that targeting according to the strict criterion. These are participants who are getting very, very close to the right answer. What we can see is that there are substantially more sign plot with text. In some ways, that's obvious. We are truly giving them more information, but it was unclear whether the participant could actually use all of that additional information. So one takeaway I have from this is that it looks like US adults could actually use sign plots just fine. Just showing people all of the data is one effective way to actually communicate, say, statistical information. Why does any of this matter? How does this connect back to engineering practice? This is an exercise I like doing with my students, which is, especially for my mechanical engineers, asking them to do things like, let's go look into material properties. Like, what do you actually find if you go searching for this kind of information? So this is a search that you could try on your own if you'd like to. Pick your favorite aluminum alloy or whatever alloy. 6061 is, we would say, garden variety aluminum. If you go and actually search, do a web search for this kind of material, what you'll find are tables that look like this. What they tend to report are just average values. This looks quite a bit like what we actually gave in the text-only treatment. In fact, what we gave is a little bit more direct than what you tend to see in this kind of engineering documentation, really directly telling them this is just an average bid, and there's actually more bids out there. With these sorts of things, we actually have to dig a little bit in order to find those caveats. So typical sometimes translates to average. It sometimes also translates to median. And also, we tend to see all sorts of other exciting and potentially scary caveats that come along with these kinds of documentation. So this text-only treatment looks a bit like some of the documentation that exists in engineering. So takeaways from this part, I would say targeting is actually pretty common. When participants have information in front of them, we saw that they're pretty readily able to guess or give an answer, not just guess, in the correct direction, and sometimes even to give us a fairly precise answer. But things like data presentation can either promote or hinder targeting. We saw that bar charts have this bar tip limit error problem that leads to some erroneous conclusions and poorer decisions. Reporting averages alone also tends to hinder targeting. And so one takeaway is to just show variability. We did that using a sign plot, but doing things like showing tolerances, just giving a plus and minus as well, can also help to disrupt that kind of behavior. So to close things out, let's talk about useful ideas for the classroom. I've got 4 short ideas that I think are implied or supported by that kind of work. So idea 1 is actually based on this progression I just showed. We can encourage our students to dig deeper. If students are going to encounter this kind of documentation that is reporting single values, why not train them to read this sort of thing critically? To start to ask questions like, well, what is this? Is this, say, an average? Is this a minimum value? Is this a maximum? I could probably be looking in the documentation to figure out what kind of number is actually being reported. I like using this particular example because my students tend to feel scandalized when they see that, oh, I'm actually not allowed to use this for design. And it gives us an entry point to talk about why we're not allowed to use this design. Actually, in an aerospace context, it would be unlawful to use these values for design because Part 24 of the Code of Federal Regulation, Title 14, Part 25, Subpart 613, actually legally requires that if you want to have an airworthy aircraft, you actually need to use lower values, something we call a basis value. That's because we need to build in that kind of safety in order to deal with that kind of statistical variability. I like to get at this when I teach data science. I actually have students do data explorations using data sets that have multiple realizations of the same material. So they can be confronted with the idea that if you go through a manufacturing process, it will not magically get stamped out as being the identical thing. John and I were talking earlier about this often comes up in, say, machining classes. There are dimensional tolerances on components. I think most programs talk about that. I think to a more uneven degree, we talk about things like variability and stuff like material properties. So because I teach a data science class, I have this opportunity to have students dig into the data. I also think that just showing these kinds of quantities with variability implied would be another way to start to disrupt this idea, or at least seed out there for our students that variability exists and it's worth thinking about. Another idea is to actually teach this targeting concept. I've tried this out actually in a professional development context. So after that first round of interviews with 24 participants, the following summer, I did a similar study, recruited more practicing engineers, but I tried something a little bit different. I designed some tasks that were actually based on these kinds of data sheets. So I presented these practitioners with data sheets that had basically single values. I didn't specify what values we were actually reporting. I wanted to see what kinds of questions engineers would ask when they were confronted with this. I did this in a pre-workshop fashion, and then I actually invited all of my participants to come and actually talk about some of the research findings from the previous round of interviews. We talked about targeting. We talked about data science and how it can be used in an engineering context. And then I came back to these participants and interviewed them again. So here's one participant. I'm going to show you both the pre and post interviews with this person. When she was working with this kind of data sheet question, and I asked her things like, okay, how would you use this to inform design? She talked about things like, okay, well, we could change the material, we could change the design. These were all useful engineering moves, but at no point did she talk about variability or ask questions like, where do these numbers actually come from? What do they mean? After the workshop, this is the conversation that we had. She talked about things like, well, this is just a single value. I'd probably ask some questions. I would ultimately want to get the minimum tensile strength because that's what I'd want to use for design. And also, this single value that you're giving me is probably not a comprehensive view of what this material actually does in practice. So she ended up seeking a minimum value. She ended up asking these really statistically flavored questions that get EETI. And ultimately, she actually invited me to give the same talk for her organization because she wanted her colleagues to get this kind of training as well. Okay, idea number 3 is you can try quizzing your students. I've taken a simplified version of the survey that we have, loaded it up into our LMS, and I've given it to them. I can't show you the results from that because that's not under an IRB, but as you might expect, my students end up targeting more. They ended up answering these questions correctly at a higher rate than random US adults perfectly. And so that ended up being an entry point to talk about not just how you incorporate variability into decision making, but since this is in a data science class, we could actually talk about things like now reporting standards. If you're going to be designing graphs as an engineer for your colleagues, what are the kinds of things that you should be thinking about? Are you going to be given by reporting things using bar charts? Maybe you should think about a different way of reporting those kinds of summaries. Final idea, and also last content, talk about what neglected variability looks like. I still come back to this example because it's very striking. I think it's very surprising at first, this whole average man idea. And it ends up really underscoring why variability matters, how things can go wrong. I know that one, I don't know if bias is quite the right word, but one preconception I had at the beginning of the project is that oh, statistical thinking is hard. People are really going to grapple with just thinking about variability in general. And I think that through this whole study, I've been a little bit humbled to find that, no, actually, people have some pretty sound everyday experience encountering variability. Where I think things are really breaking down is at the reporting stage. Or put differently, if there's anything I think that we need to work on, it's helping our students recognize that variability could exist. And once they have that underlying inclination, then they can basically handle a lot of the rest of it on their own. Some thanks and acknowledgements I need to give. This is work that was funded by the National Science Foundation under this particular number. I've worked with a number of undergraduate research assistants over the years. Some of them are pictured here and named. And my primary collaborator on the survey is Professor Jeremy Wilmer over at Wellesley. He's a professor of psychophysics. So he has like a very, very deep training in this kind of instrument development that I've gotten to benefit from. And the instrument that we've developed would not have taken the shape it did were not for his thoughtful work. I think that is now all that I've got. There's one more slide here, which is the references slide. And hopefully we still have time for questions.
Please join me in thanking Dr. Del Rosario.
It's kind of inside, you kind of interview aerospace, civil, and mechanical. Can you find any factors in there that are better variability?
Did we notice any differences across those disciplines? So yes, some caveat. So first thing I'll say is that sample size there was pretty small, so only 24 participants. It's also somewhat unbalanced. When it comes to like our ability to detect finer grain differences, that really wasn't there by design. There was one thing that I think was strikingly different. There was one task we had, which was, I think I'll punt describing the sphere task to make sure I give a succinct answer. Basically, there was one task that really came down to an idea of iteration, like iterating on a design. And what we found is that our mechanical and our aerospace engineers tended to come to that as an approach, whereas our civil engineers often will kind of just stand flummoxed, like, I know this isn't going to work, but I'm not sure what else I could do. And I think that's something that's actually quite... It's a striking difference in practice where with civil engineers, like a lot of them in our interviews talked about how like we don't get a test building. You don't get to go and like build a practice building and then go actually build the real thing. Whereas in things like in mechanical and in aerospace, you often do. You get to do prototyping. And so there are these real differences in practice that led to pretty strikingly different approaches, even at the level of data analysis. Sure.
I guess maybe your thoughts on how to move further beyond that targeted and why I'm asking that. In my class, right now, they did basically a whole lesson on how you interpret data and the nuance.
That is awesome. And I'm so glad, just to make it clear, I'm probably not talking to you when I make those kinds of recommendations about like to bring in data because you're already doing these kinds of excellent practices.
Like, yes, we need to consider women and further variability in physical characteristics generally, but then moving past that statistical representation, like seatbelt design is designed to hit where a woman's uterus is. So whenever you're pregnant, there's a much larger probability of you having, or actually there's a much larger chance of you having fetal injury risk in even a minor crash because of where the seatbelt hits.
Yeah.
So like how to encourage thinking beyond maybe what data will show to consider things past that that are important in design?
Yeah, it's a good question, sort of going beyond sort of the question is the probability of the particular occurrence that I have in mind here, actually thinking beyond what other types of things could happen. Yeah, with the project, just given how tricky variability is, this project was very interested in, especially looking at now, like limitations of what I can actually speak to or give useful comments on. Like the kind of problem you raise here is why the thing I'm looking at next is mathematical models, like models, and especially assumptions that we make whenever we set up whatever approach we're using to make sense of an engineering system. That's actually like, as I'm kind of winding down this arm of my work, that's what I'm starting to think about next. And so the framing that I'm starting to adopt is really thinking about how we can train our students to recognize the kind of assumptions that are getting built into the analysis or the approach that they're taking, and especially connecting it back to limitations of that. So for instance, an assumption that we're making is that, okay, we're only looking at injury to the passenger themselves. Well, maybe we need to think beyond that. Maybe we need to think about, well, what if there's actually, say, additional living beings that are, now in the system as well, thinking about, say, pregnant people. That I think starts to gesture in that direction, but I'll be the first to admit that line of my work is super nascent. So I don't have like a lot to give you quite yet. Mhm. I teach a whole responsible for our first year course on mathematical modeling. And what I do is I take, it's very much a constructivist approach where I want students to be not just learning off-the-shelf analyses or models that other people have developed, but actually to be responsible for designing their own models, and especially aligning the question that they're trying to answer with the model that they're building. I find with that approach, especially as I was handed responsibility for this class and sort of took more ownership of it, when we focused more on, say, that linkage between question and model, we see students actually take more agency, and also start to attend to assumptions in a more authentic way. A failure mode I used to see with this kind of class is students would kind of want to show off. They'd like want to build the most complicated model possible, and then they'd run out of time at the end because they're first year students and they don't actually have time to do a whole PhD. Where I want to get students to is identifying what are the key things that they need in the model to answer the question as posed, and to make sure that those things are aligned. So with something like, say, safety of an individual, that might suggest that we need to broaden our scope of what we're actually considering in the model. Say, not just the safety of a passenger, but maybe safety of, say, an unborn child inside them, that sort of thing. Mhm.
So one of the things I noticed that struck me as a difference between the example survey question and the example that you gave for your students in class was that the survey question was framed as like, out of 100 bits, there's this average. Whereas if I go to a website and look at the tensile strength of that aluminum, it just says, this is the tensile strength.
Yep.
And so did your survey include any questions that sort of had that authoritative language that affected people's targeting variability?
In this survey, no. Let's see if the clicker still works. So in this qualitative study now, in the interview, we did do that. We did present participants with, say, this authoritative looking presentation of the information. And this is the kind of thing that we saw. A lot of our participants didn't even ask questions about, say, should I trust these numbers or not? When I teach data science, one of the underlying ideas I'm trying to get at is curiosity balanced by skepticism. And I think that if students can come away with that mindset, I think they're already equipped with a lot of what they need. What I didn't see looking at the data in a lot of these pre-workshop interviews was that kind of skepticism. And it was only after the workshop that we saw with, some, not all participants, but some of them would actually start to ask qualitatively different questions. Things like, actually, where did this data come from? Should I trust this number? What is the summary that you're reporting here? We haven't gotten a chance to do inferential work with that yet. It's a kernel of an idea that I would like to unpack later, but with this kind of instrument that we've developed, this is the first thing we have that we trust. And part of the idea from here is to start to build and start to fill out the space of questions that we can actually pose. Oh, sorry, questions that we can hopefully answer. Over here. Yeah, it's like in a very true sense, it represents no one. Mhm. 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 Yeah. That was actually that was my previous life. So like my origin story. Yeah. No, it's exactly that. Yeah. And so my PhD was really in reliability analysis. And the dirty secret about reliability is that it's not about making things safer. It's about making things controllably less safe so that they're more efficient. It's what people don't usually tell you until you start working in this space. Um, it my I've done more like literature review, mostly out of my own curiosity. So I used to on safety factors, like the history, what are some examples? And I think one of the things is most striking. My training is primarily in aerospace, but I have gotten a chance to chat with a lot of civil engineers, and I am in awe of the soundness of the civil, or especially the structural engineering approach. Because in aerospace, our primary safety factor is 1.5. There's open disagreement about where it actually comes from or what it does. Like, it's kind of a historical quirk, and people still disagree on what it actually accomplishes. But in civil engineering, one of the forms of code is called load and resistance factor design. Engineers end up using all these tables and they reference these factors and use them in design houses. But actually back in the 80s, there was a research team that went through and quantified, here's the variability that comes from materials. Here's the variability that comes from manufacturing, basically from job to job site, say how the concrete is poured. They rolled all of that up into calibrating those factors so that they can actually achieve known reliability targets. So they know exactly where those factors came from, and they're very defensible. Quite a gulf between aerospace and structural engineering practice, though. I tried advocating for those sorts of things in aerospace. I was not successful. Well, then your discipline is actually, I think, the gold standard of this sort of work. You're very welcome. Olin only offers degrees in mechanical, electrical, and computing and general engineering. So I haven't any aerospace content. I've migrated more to sort of these stuff anyway. This is the thing that has really captured my heart and my attention.
Where can I get like,
Sorry?
find this part of the book? Where can I find this slide?
Where can you find that slide? I mean, if you send me an email, I could send you some of this stuff. I don't know where the figure came from. The book that I reference that talks about a lot of this stuff is by Todd Rose. It's called The End of Average. I forget the subtitle, but if you put in Todd Rose End of Average, you'll get what you're looking for. Mhm.
Final. Rosario. All right, well, please join me in thanking Dr. Del Rosario once again. As always, let's please be good stewards of the space. If you have food waste, please deposit it in one of the red bins in the corners on this side of the room. We have a few unclaimed lunches over there. Please feel free to grab them on your way out, and I hope you all have a wonderful rest of your day.
Thanks, folks.